Assalamualaikum and hi everyone. Today we are going to continue our lesson for the subtopic 13.3, which is the molecular kinetic energy and internal energy. The outcomes for the subtopics are: at the end of this chapter, students should be able to first discuss transnational kinetic energy of molecules. Second, discuss degree of freedom F for monoatomic, diatomic and polyatomic gas molecules. Third, state the principle of equipartition of energy. Fourth, discuss internal energy of gas. Fifth, solve problems related to internal energy. 13.3 molecular kinetic energy and internal energy. Look at the molecular kinetic energy. From equation of P equals to 1 over 3 nm over V times means squared of velocity. Then rearranging the formula, we will have the P, the pressure, equals to 2 over 3 times n over V times 1 over 2 m times mean squared of velocity. Now we can see that this equation shows P will be increased when the n over V increases and 1 over 2 times m times mean squared velocity increases. By rearranging the equation of 13.5, so we'll get the PV equals to 2 over 3 times n bracket 1 over 2 m times mean squared of velocity, right? And we know that the PV equals to n kt, and the other ones we notice also the PV equals to n, the small letter of n times r times t. Okay, from the equation of just now, we can see that the nkt equals to 2 over 3 times n bracket 1 over 2 m times mean squared of velocity. And then by rearranging the formula, we'll get the ktr equals to 3 over 2 times kt equals to 3 over 2 bracket r over na times t, where the k equals to r over na, where the KTR is actually the average transnational kinetic energy of a molecules in the container. T is absolute temperature, B and K Boltzmann constant, R molar gas constant, and Na is Avogadro constant. For n molecules of an ideal gas in the cubical container, the total or average transnational kinetic energy E is given by equation E equals to n times KTR. KTR is the transnational kinetic energy. And then by rearranging the formula here, for the KTR equals to 3 over 2 of K times T, we get the equation of energy here, E equals to N times bracket 3 over 2 K times T. And then now we get the equation, the energy for the molecules in the container equals to 3 over 2 N times K times T, or it also can be written as E equals to 3 over 2 times n small letter of n times r times t. The second one, degree of freedom, the F. What is degree of freedom? Is defined as the number of independent ways in which an atom or molecules can absorb or release or store the energy. For the monoatomic gas, example He and E dan AR. The number of degrees of freedom for this monoatomic gas is 3, where the 3 direction of translational motion contributes transnational kinetic energy as shown in figure 13.6. Okay, look at the figure 13.6. We have the helium atom here, He. Okay, this atom can be moved to the X direction, Y direction, also for Z direction, or along X, Y, and Z axis. So that's why it has the 3 degrees of freedom. For the diatomic gas, example hydrogen, oxygen, and lithium, and the number of degrees of freedom is, okay, look at the hydrogen atom. Okay, this hydrogen can move to the X direction, Y direction, and Z direction also. So that's why it has, for the transnational kinetic energy equals to 3, and then it has also the rotational kinetic energy, okay, for the Y axis and Z axis. So that's why it has 2 rotational kinetic energy. So total up for the degrees of freedom is 5. For the polyatomic gas, example H2O, CO2, and H3, okay, the number of degrees of freedom is given by, look at the figure 13.8. So it has the 3 transnational kinetic energy, and then it has also the 3 rotational kinetic energy. Okay, so here we'll get the degrees of the freedom or the kinetic energy is 6. Okay, so now this table shows the degrees of freedom for various molecules at the temperature of 300 Kelvin. For the monoatomic, example helium, the degrees of freedom for the transnational is 3, rotational is 0. So total up is 3. Average kinetic energy per molecule is 3/2 times K times T. For the diatomic molecules such as H, hydrogen, transnational 3, rotational 2, and total up 5. So average kinetic energy per molecule is 5/2 times K times T. For the polyatomic molecules such as H2O, it has 3 transnational degrees of freedom. Okay, and it has also 3 transnational degrees of freedom for the rotational degrees of freedom. The total up is 6. So the average kinetic energy per molecule is 6/2 times Kt equals to 3 Kt. Degrees of freedom depending on the absolute temperature of the gas. For example, for diatomic gas, look at here for the figure 13.3, hydrogen gas have the vibrational kinetic energy where it contributes 2 degrees of freedom, which correspond to the kinetic energy and the potential energy that associated with the vibrations along the bonding between the atom. And then look at the temperature. When the temperature 250, the monoatomic, it has degree of freedom is 3. For the diatomic is monoatomic, for temperature of 250 until 750, for the monoatomic is 3, and the more than 750 Kelvin, for the monoatomic degree is also 3. But for the diatomic, for the temperature of 250 Kelvin, it has 3 degrees of freedom. For the temperature of 250 until 750, it has 5 degrees of freedom, and more than 750 degrees, It has 7 degrees of freedom. For the polyatomic molecules or atom, okay, for a temperature 250 Kelvin, it has 3 degrees of freedom. Okay, for the temperature 250 until 750 Kelvin, it has 6 degrees of freedom. And if the temperature is raised or increased to more than 750 Kelvin, the degrees of freedom for the polyatomic will be higher, which is the X. Okay. So this is the depending on the temperature. 13.3.3 Principle of equipartition of energy states that the mean or average kinetic energy of every degrees of freedom of a molecule is equals to 1/2 kT. Means, or therefore, the transnational kinetic energy equals to F/2 times K times T. Okay, so this is the mean or average kinetic energy per molecules, whereas we have another equation here, the K equals to F/2 times R times T in terms of average or means kinetic energy per mole. Okay, F equals to degrees of freedom and T is absolute temperature. Right? K is the molar gas. Sorry, R is for the molar gas constant. Look at the example 13.5. A vessel contains hydrogen gas of 2.2 times 10 to the power of 80 molecules per unit volume, and the mean square speed of the molecules is 4.5 km per second at a temperature of 50 degrees Celsius. Determine A, the average transnational kinetic energy of a molecule for hydrogen gas. B, the pressure of hydrogen gas. Given the molar mass of hydrogen gas equals to 2 gram per mole, Avogadro constant 6.02 times 10 to the power of 23 per mole, and K, Boltzmann constant, equals to 1.38 times 10 to the power of minus 3 joule per Kelvin. So in order to solve this question, we need to take out the information that given in the question, which is the N/V, which is the molecules per unit, equals to 2.2 times 10 to the power of 18. The mean square of velocity equals to 4.5 times 10 to the power of 3 meter per second, and the temperature here is 323.5 Kelvin. Given in the degree Celsius, 50 degrees Celsius, we need to plus up with 273.15 in order to get the temperature in Kelvin. By using the equation of transnational kinetic energy, KT equals to 3/2 times KT. 3 here is because of this is the hydrogen gas, so it has the 3 degrees of freedom here. Okay, by putting the number of K and T in the equation, so we get the average transnational kinetic energy of a molecule is 6.69 times 10 to the power of minus 21 joule. Right. B, the pressure of hydrogen gas. Okay, we are using the formula P equals to 1/3 N over V, because N over V is the number for volume, times M, and times the mean square of velocity. Just putting the number in the equation here. Okay, and then we know that the M here is equals to M over NA, which is M is the molar mass of molecule. Okay, over NA. Okay, by putting the number in the equation, we will get the answer for the P is 1.10 times 10 to the power of minus 5 Pascal. Example 16.6. A vessel contains an ideal polyatomic gas at temperature of 30 degrees Celsius. The total transnational kinetic energy of the gas molecules is 6.00 times 10 to the power of minus 6 joule. The mass of the gas is then doubled up and the total transnational kinetic energy of the molecules become 13.00 times 10 to the power of minus 6 joule. Determine the new temperature of the gas. Right. So we take out the information given in the question. The temperature 1, which is the initial temperature, is the 303.15 Kelvin, where 303 here comes from the degrees in the Celsius plus 273.15 Kelvin. Okay, and the energy initial equals to 6.00 times 10 to the power of minus 6 joule. Energy when it raised up or double, okay, E2 equals to 13.00 times 10 to the power of minus 6 joule. And then the mass, final mass equals to 2 times of initial mass. It is given and then double, right? Alright. So by applying the equation of total transnational kinetic energy, the E equals to 3/2 NKT. Okay. And we know that the N, the number of molecules, equals to the mass over molar mass times Na, which is Avogadro number. Okay. Then we put the equation here. The E equals to 3/2 M over M, capital M, times Na, the Avogadro number, and times R over Na of T. Now, the E equals to 3/2 M, the mass of the molecules, gas molecules, over molar mass, times R, the molar gas constant, times T. And here can be eliminated, right? Okay, that's why we get this kind of the information equations. Okay, so just put the number in the equation for the temperature T1. Okay, E1 equals to 3/2 times M1 over M times R times T1. And then for the temperature T2, when it's raised double, E2 equals to 3/2 M2 over M. And we know that the M2 here is equals to the 2 times M1. Okay, and then by equating these two formula, is these two equations, E2 over E1 equals to 2 times of T2 over T1. So we just get this time of equation here, then we get the temperature for the final temperature T2 equals to 328 Kelvin. So here's the answer for this question number B. Okay, now we go to the internal energy, the U. Is defined as the sum of total kinetic energy and total potential energy of the gas molecules. Okay, and then we know that because of other gas, the intermolecular forces are assumed to be negligible. Thus, the potential energy of the molecules also can be neglected. Then, for the N molecules, we can have the internal energy U equals to N times the mean square of transnational and kinetic energy. Okay, so we can have U equals to F/2 and KT, because we substitute this K here, KTR is F/2 and KT. Okay, now we can have the equation here, U equals to F/2 and RT, since we know that the K equals to R over Na. The K is Boltzmann constant equals to molar gas constant, the R over Avogadro number, and then we get this kind of the equation where U equals to F over 2 and RT. Okay, so we know that the U is internal energy of the gas. So this table shows the properties of 1 mole of an ideal gas for the relationship between degrees of freedom for the 3 type of gas: monoatomic, diatomic, and polyatomic. Okay, so for degrees of freedom for the monoatomic is 3, diatomic is 5, and polyatomic is 6. This kind of degree of freedom. And then for the average kinetic energy per molecule for the K, average kinetic energy per molecules for the monoatomic is 3 over 2 times kT. For diatomics, 5 over 2 times kT. Then polyatomic is 6 over 2 times kT, or equals to 3 kT. And then the third one, internal energy U per mole. For the monoatomic, we have the equation here, 3 over 2 times RT. For the diatomic, 5 over 2 times RT. And then for the polyatomic, 6 over 2 times RT, or equals to 3 RT. Example 13.7, we have 2 moles of an ideal monoatomic gas in a closed container at constant volume is heated until its pressure is doubled. Now pressure is doubled. If the final temperature of the gas is 750 Kelvin, calculate the initial temperature of the gas. Initially, how much temperature of the gas? B, the change of the internal energy of the gas. Given that the R is the molar gas constant equals to 8.31 joule per Kelvin per mole. Okay, given in the equation n equals to 2, P2, the final pressure is 2 times of initial pressure P1, and T2 is the final temperature equals to 750 Kelvin. Okay, we will use the equation of Gay-Lussac law because why? The constant volume. Constant volume, we will use the Gay-Lussac law. Okay, we have the P1 over T1 equals to P2 over T2. Just and then substitute the P2. P2 is double of P1. So P1 over T1 equals to 2 times P1 over T2 is 750 Kelvin. Now we have the initial temperature for the system is T1 equals to 775 Kelvin. This is the answer for the A. And then for the B, the change of the internal energy of the gas after the pressure is double. Okay, so the changes of internal energy equals to the final of internal energy minus the initial internal energy. Okay, and then we will substitute the U here in the equation. U for the final internal energy is F over 2 times N R T2. T2 is the final temperature, and then minus F over 2 and R T1. T1 is the initial temperature. So we will substitute this number in the equation. Okay, and then we'll get the answer here for the changes of internal energy is 9.35 times 10 to the power of 3 joule. Okay, that's all class. Thank you very much.